Welcome to section 3.1, Basic Functions and Their Graphs. So far in this course, we have looked nearly exclusively at linear functions. We've seen a few examples of nonlinear functions, but in this section we are going to greatly expand on our library. There are several families of functions that are introduced in the notes, beginning on page 37, that we will want to familiarize ourselves with. These functions are going to be the basis for many more functions to come later in this section and later in the course. So the first one that we see is the square function, f of x equals x squared. Now, one way of arriving at the graph of this, and the way that we will have to use to begin with, is by completing a table. So plugging in x values, seeing what y values we get out, and trying to extrapolate a pattern from the results. Now, before we begin plugging in x values, we need to consider what x values we might be able to plug in. And looking at what this function does, f of x takes the x value that we assign, and it squares it. Now, thinking of numbers that I'm able to square, I'm unable to come up with any that I cannot square. I can square 0, I can square 5, 1,000, I can square negative numbers, anything goes. So if I plug in 0, f of 0 would be 0 squared, which is 0. If I plug in 1, f of 1 would be 1 squared, which is 1. If I plug in 2, 2 squared would give me 4. If I plug in 3, we would get 9. If I plug in 3.5, you can plug that one in your calculator, we would get 12.25. And if I plug in 4, I would get 16. So these are just a sampling of the x values that we could plug in and the resulting y values that we would find. We can also go in the negative direction. Negative 1, if I square that, I would get 1. Negative 2, if I square that, I would get positive 4. Negative 3 would give me 9, and we can see sort of a symmetry going on. If I square 2, I get 4. If I square negative 2, I get 4. So really, all I need to do is look at the positive x values, and then I'll know what would happen for the negative x values as well. So with these points, we'll start trying to come up with a graph. Our function does not give us any negative outputs, so I will expose more of the upper half of the xy plane. If we plug in 0, we got 0. If we plugged in 1, we got 1. Plugging in 2 gave us 4. Plugging in 3 gave us 9. Plugging in 3.5 gave us 12.5, so let's put 4 right there. 3.5 would be somewhere in this neighborhood. And 12.5 would be somewhere right around there. So we get that point. Plugging in 4 gave us 16. And if you're doing this on graph paper, you can really start to see the shape of this curve if your points are good and accurate. Going in the negative direction, negative 1 gave us 1, negative 2 gave us 4, negative 3 gave us 9, and so on. Negative 4, if we had gone that far, would have given us 16 as the output. And so the shape of this curve is this nice bowl shape, which you've probably seen before, the parabola. So there we have the graph of our square function, as we call it in the text. You can see, based on our inputs and based on thinking about what the function does, that our domain is all real numbers. But our range, we're never able to output any negative numbers by squaring numbers. So our range begins at 0 and goes up from there. And that is how we can figure out what the graph of this function looks like. We can follow a similar procedure to arrive at the graph of x cubed, which you'll see on the next page of the notes. Now that function, if you cube a positive number, you'll get a positive number. If you cube 0, you'll get 0. And if you cube a negative number, you'll get a negative number. So any positive or negative number can be cubed, and we can arrive at any positive or negative number, and that is why for the cube function on the next page, we have a domain of all real numbers and a range of all real numbers. Now it's worth noting that the x values that I chose to plug in for x squared here were chosen purely for convenience. These are nice numbers to work with. But if we go to the table, if we plug our function x squared into the graphing calculator and go to the table, make sure that your table set is on auto. Instead of having the delta, the step size, be 1 unit, I'm going to have a step of 0.25. Now if I go to my table, we can see an input of 0 gives an output of 0. But an input of 0.25 gives an output of 0.0625, so a very, very small number. An input of a half gives an output of a quarter. An input of 3/4 gives us an output of 0.5625. If we make our step even finer, if I go back to the table and I have an input every tenth, every 0.1 units, you can see how the outputs would change in that case. So the fact that I chose to use 1, 2, 3, 4 as my inputs does not detract from the fact that I could have used any x values. So this function is continuous. It exists over the whole of the x-axis, and we always get an output. And that accounts for the smooth curvature of our graph. We can do the same type of thing with our other functions. I'll put my table back to having a step every unit. And I'll change this to x cubed, and we can see what the table looks like for that guy. So here we have 0 giving us an output of 0, 1 gives us an output of 1. Now here is where we start to see a bit of a difference. 2 gives us an output of 8, 3 an output of 27, 4 gives us an output of 64, so we can see the growth here is much more extreme than it was for the square function. If we look in the negative x direction, we can see -1 gives us an output of -1. If you cube -1, you get -1 back. But if you cubed -2 times -2 times -2 would give you -8. -3 gives the output -27. -4 gives us -64. And -5 as the input gives us -125. So we can see how this function goes upwards to the right and downwards to the left when we look at the graph. And that's reflecting those points that we found using the table. Now again, this function exists over the whole domain from -infinity to infinity. So it doesn't just exist at these discrete points, it exists everywhere in between. If we look back at the table and we change our settings so that there's a tick mark every 0.1 units, we can see something odd. So when our input is 0.1, our output is 0.001. When our input is 0.2, our output is 0.008, pardon me. So when we're very close to 0, our outputs are extremely close to 0, much smaller than the input that we started with. The closer that we get to 1, the closer our outputs get to 1, but the growth is very gradual, right? We go from 0.008 to 0.027, 0.064, 0.125, 0.216. These are not growing very quickly. If you were to really zoom in, which we can do on the graph, zoom way in fact I'll change my window so it goes from -1 to 1 with an x scale of 1, so I won't have any tick marks getting in the way. And we'll go from -1 to 1 vertically as well. That gives us a nice perspective on what's happening on the very small scale with this function x cubed. I'll put x squared up again so we can see what that looks like in this same scale, and there we see it looks just like a parabola. So our growth for the parabola, for a little while at least, the parabola is actually above x cubed, but then if we zoom back out, zoom standard, we can see that our x cubed quickly outpaces x squared once our x values get outside of that -1 to 1 range. So just a couple of interesting little facets of these graphs. Now for the other functions in this section, we'll do the same kind of thing for the function for the square root function. Again, we would like to know what type of x values we can plug in, and we've already discussed the square root. We know that x cannot be less than 0. So our domain is 0 to infinity. And if we think about what the square root does, right, if the square root takes in a positive number, it's going to return the number which is the square root of that number. We always end up with the principal square root. For instance, the square root of 4 is 2. The square root of 0 is 0. The square root of 9 would be 3. The square root of 16 would be 4. So we can see as our x values increase, our y values also increase, the smallest being 0. So our range is the same as our domain. So I will rely on the calculator to do the heavy lifting from here on in. If I clear out the functions that we had in there originally and I plot the square root of x, I'll go to the table and we can see that for every x value in the negative side, we get an error. And that's because there is no real number that the calculator can output when I plug in -1, for instance. So there we can see what's going on with our outputs. For those positive inputs, if I input 1, I get 1. If I input 2, I get this big long decimal. If I input 3, I get another big long decimal, slightly larger than the last one. And finally, if I plug in 4, I get 2, the square root of 4. So if we continue on, an input of 9 gives an output of 3, an input of 16 gives an output of 4, and so on. Go out a little further, 25 would give us an output of 5, and so on. So if we go to the graph, we can see all of those points plotted. Here we have 0, 0, 1, 1, 4, 2, 9, 3, And if I extend my window out a little further, if I go out to, say, 25 horizontally, I don't really need to be able to see very far to the left, so I'll just start at -1. Let's see what our graph looks like. There we have it. Gradually increasing. The further out I go, I have to go out a little bit further each time to find one of those nice x values that gives me a nice y value. So 2, then 4, then 9, then 16, then 25, 36 if we went out a little further, 49, and so on. And that is the shape of our function x squared, or sorry, the square root of x. We can do similar procedure for the cube root of x. Now the cube root can take in negative values, right? The cube root of -8 will give me -2, just like cubing -2 gives me -8. So there, if we change our function, now I have to hunt around for the cube root, it's under the math menu. The cube root of x, and I'll go to the table again. If we start at 0, we can look and see that the cube root of 1 is 1. The cube root of 2 is something weird. In fact, we don't come across another nice input until we get down to 8, the cube root of 8 being 2. We've got to search for quite a while longer until we get down to x equals 27, which gives us an output of 3. Remember that 3 cubed is 27, so the cube root of 27 is 3. Now, if we go back up to 0 and look in the negative direction, we can see that -1 gives an output of 1, so we don't see any more of those errors. But we do still have to search quite a ways, down to -8, before we get a nice output. Now, these inputs are not invalid, they just aren't very good to work with. So -2, -1.2599, that's a tough point to plot. So when you're graphing these by hand, you like to find these nice points like -1, -1, 0, 0, 1, 1, 8, 2. Stuff like that is easy to plot and easy to see the general shape of the graph. Speaking of which, let's look at what this graph looks like. And I'll go back to a standard zoom. And we can see some slightly odd, an odd looking function. It kind of increases slowly until it gets to about 1, and then it sharply increases and then slows down again. Let me tweak my window. Remember, we had to look pretty far out to the left and right before we could see any good points to grab a hold of. So I'll go from -30 to 30 with ticks every 5 horizontally. And there we can see a little bit better picture of our graph. So that is the cube root function. Looks pretty similar to the square root function, except it does exist to the left of 0. Now, those are the first two families. We saw the polynomial type functions, the square, the cube, and then we saw a couple of radical functions, the square root and the cube root. Those are the only ones that we're going to worry about of those types for the time being. Our next type of function is a totally different animal, and it's the absolute value function. So again, before we get to start coming up with points, we need to know what x values can potentially be plugged into this function. And thinking about what the absolute value does, it takes numbers and returns the positive version of those numbers. So if we plug in 0, the absolute value of 0 is 0. If we plug in 1, we would get 1. If we plug in 2.35, we would get 2.35. So not a lot of work to be done here. If we plug in 80, we would get 80. So just choosing a whole bunch of numbers at random. Now if I go in the negative direction, if I plug in -1, the absolute value is going to turn that positive. If I plug in negative 3.6, the absolute value is going to turn that positive. It'll have the same magnitude, though. Negative 61 will return positive 61. So if we plug that function into the calculator, again, the absolute value isn't one that is right on the front face of your calculator. If you look under the math menu, you actually have to click over to the number tab. There's the absolute value function, and we'll put our x there. And I'll go to the table and we'll see exactly that behavior that we just described. If I plug in 0, I get 0, plug in 1, I get 1. Plug in any positive number and the output is going to be exactly the same as the input. If we go in the negative direction, the output will be exactly the same, but positive of what we plugged in. Now graphically, how does that manifest? Well, if I plug in 0, 0, that would be on the origin. If I plug in 1, 1, there's that point, 2, 2, just beyond it. And we can kind of see how this looks just like one of our regular lines with slope of 1. And that sort of behavior will continue. In the negative direction, we get the positive version of our input. So negative 1, 1, negative 2, 2, negative 3, 3, and so on. And so the function produced, if we bring the calculator back, if we go to the graph, the function produced looks just like a V. So I'll use a standard zoom and then a square zoom to illustrate just how sort of perfect looking this graph is. If you're using graph paper, it should look exactly like a V. There should be 90 degrees between your two legs of the function. And that is our absolute value. Now, just as with all of our other functions, we already talked about the domain. Looking at the graph of this function never returns any negative y values. It only returns positive values or 0. So our range here, just like for the square function, is 0 to infinity. But for slightly different reasons. This function turns numbers positive. The square function returns positive numbers, but they're not exactly the same as the number that we input. The next function that I'd like to look at is, in my opinion, one of the more interesting functions in this section. So this function, 1 over x, we know that x cannot be 0. Right? We don't want our denominator to be 0, so right off the bat I notice that there is a concern with the domain. The domain of this must exclude 0. Any other input, however, is fine. Positive numbers, negative numbers, fractions, decimals, anything goes except for 0. So, if we start trying to input some values and see what that gets us, I can't start at 0 as I have for all these other functions. So I will start instead with a half. So what is 1 over 1/2? Well, we can use some keep change flip type action and say this is 1 times 2 over 1, which is 2. So if we plug in a half, we get 2. If I plug in a quarter, I would get 1 over 1/4, which, if I keep change flip, would look like 1 times 4 over 1, which is 4. So 1/4 returns 4. If I did 3/4, 1 over 3/4 would actually be 1 times 4/3, which is 4/3. And finally, if I plug in 1, we get something a little less funny looking. 1 over 1 is just 1. Alright, so I've dealt with some of the trickier x values. Now let me go a little bit further out. If I plug in 2, 1 over 2 is a half. And if I plug in 3, 1 over 3 is obviously 1/3. 1 over 5 would be 1/5. 1 over 10 would be 1/10. So we can see how these fractions as outputs are getting smaller and smaller the larger our x values get. When our x values were very small, we got relatively large y values. And as our x values increase in size, our y values seem to be decreasing in size. That kind of makes sense, right? 1 divided by a larger and larger number is going to return a smaller and smaller value. If I go in the negative direction, if I plug in -1/4, 1 over -1/4 would look pretty much the same, except it would be negative 1 times 4 over 1, so -4. 1 over -1 would give me -1. 1 over -10 would give me -1/10. And so we can see again this sort of symmetry. Whenever I plug in a version of 10, I get 1/10. If I'm plugging in the positive 10, I get positive 1/10. If I plug in -10, I get -1/10. And that same sort of behavior is true for any potential x values that I look at. So I'll plug this function into my grapher, just as we did with all the others, 1 over x. And I'll look at my table first. So if I start at 0 and go up by, let's go up by quarters. There we see the error when we try to plug in 0. The calculator doesn't like that. If I plug in 0.25, 1 over 0.25 would give us 4. 0.5 gives us 2. 0.75 there gives us the 4/3 that we were talking about. 1 gives us 1. 1.25 gives us 0.8. And we can see the further out we go horizontally, the smaller our x value or our y values are getting. So if I go back to my table and I plug in some really large steps, if I go by 5s, there we have our error at 0. 1 over 5 is 1/5, is 0.2. 1/10 is 0.1. 1/15 is 0.666666, etc. 20 gives us 0.05, 0.04, 0.03333, 0.02, and the further out we go, if we get really extreme and have a tick every 100 units, we can see how quickly this function gets down to almost 0. So 100, 0.01, 200, 0.05. If I go down a little ways, we start seeing scientific notation, which is in the Getting Started section of the notes, if you would like to brush up on that. And if I change my table one more time, so I have ticks every 1,000 units, you can see the scientific notation starts even sooner. Eventually, our calculator will get tired of doing these minuscule calculations. We'll eventually just return 0. Even though the output is never actually 0. We're always getting a positive number, as long as we're dividing by a positive number. And we would always get a negative number, a very, very, very small, minuscule negative number, if we're dividing by negative numbers. The only thing that we can't actually get as an output is 0, because when is 1 over x equal to 0? Well, that happens when 1 equals 0 times x, if I cross multiply. And on the right-hand side here, I have 0. So this occurs when 1 equals 0, and I think you'll agree that that never happens. So our range, we can get any positive or negative number as big or as small as we want. So negative infinity to 0, 0 to positive infinity. The only thing that we cannot output, we cannot ever get or hit vertically with our graph, is going to be 0. So if we take some of these points that we've been looking at on our crazy tables and we plot them, we would see the general shape of our graph, and I'll zoom in a little so we can see a nice picture of this. Let me zoom from negative 6 to 6 and negative 6 to 6. Alright, so there we can kind of get an idea of all of these small values that we found early on. 1/4, 4, 1/2, 2, 1, 1, there we see, right there. Some of these are a little easier to see if you use a square zoom, so take what you've got and zoom square. If we go out in the positive direction, we see 2, 3, 5, giving us the smaller and smaller outputs, the lower and lower our function goes. Now one trick that you can use to kind of see how the relationship between the inputs and outputs works is to use the trace button. I really like the trace button. When x equals 0, by default it starts at x equals 0. We see that y equals nothing. So what trace does is it puts the little cursor on the graph of your function. So we can trace along it, and in fact you can plug in your x values of interest and it'll jump exactly to that point. Maybe we're interested in 4.25, a quarter. Let's see, 5. There we see 0.2, and you can see how that point, that cursor, is getting closer and closer to the y, or to the x-axis. So this is a kind of an interesting function. I would recommend playing around with it in your calculator, looking at the table, and really trying to digest how we get all these strange points. This is, I think, the most unusual function in this section. So jumping from that arguably unusual function to a much more pedestrian one, we've seen this guy before. F of x equals x. This is the last of the basic functions, and we call this one the identity function, specifically because it returns whatever we plug in. So if we plug in 2, we're going to get 2 right back. If we plug in 0, we're going to get 0. If we plug in 6, we're going to get 6. If we plug in negative 9, we're going to get negative 9. It doesn't really do anything interesting. It just takes what we give it, and it gives it right back to us. Now, from previous sections, from chapter 1, we could say that another way to write this, f of x equals x, we can think of this as a linear function. So here we have m being 1, and we have no constant, so we would say that the y-intercept b is going to be at a height of 0. So the graph of this one is pretty straightforward. You can come up with it either using a table or by recognizing that we're just talking about a very simple line. We plot 0, 0, 1, 1, 2, 2, negative 1, negative 1, and so on. Here we have our slope of 1 and our y-intercept of 0. So that is our identity function. Very straightforward. We know these lines have a domain of all real numbers, and we see this one extends up forever and down forever, so we also have a range of all real numbers. And that's the last of our basic functions. You're going to want to be very familiar with these, because now that we have the most basic example of each family of functions, cubes and squares and square roots and cube roots and so on, we are going to be able to build more interesting functions that resemble these basic functions.